So in the previous video, we talked a lot about this concept of ligands whenever you have a transition metal ion, and that the ligands are molecules that possess lone pairs, and they can those lone pairs can be donated to that ion to make these what are called complex ions. All right, so whenever you have these transition metal ions in solution, you don't actually have the free ion surrounded by whatever your solvent is. You actually have this larger complex ion, which is actually the thing that is dissolved. All right. In this video, what I want to do is talk about what makes these things special. All right. There's a special property that these things have, and it's due to this thing called D-orbital splitting. All right, and this is sometimes also referred to as crystal field theory, but I believe that the IB refers to it as D-orbital splitting. All right, so let's go back and recall that we know that atoms that contain d orbitals. All right, so we know that whenever you have an s orbital, there's one of them. When there's p orbitals, there's 3 of them, and then when there's d orbitals, we know that there's 5 of them. All right, and these d orbitals, they do have shapes. They're kind of complicated. So really quick, so here are the shapes of those d orbitals. All right, and the way that these things are named, you have to have a coordinate plane as a reference point. All right, so if we have an x, y, z set of coordinates here, the names of these d orbitals are given here. So 3 of them are fairly similar. All right, this is the d yz, dxz, and dxy. And essentially, whenever you have these 2 letters, what that would mean is that the lobes of these orbitals would actually be between those axes. All right, so for example, this is yz. All right, so this is what they're calling the z-axis, and this is the y-axis. And these lobes, notice how they're in between those axes. All right, same thing here. These lobes are between the x and the z axes, and same thing over here. All right, 2 of them are kind of different. All right, although these this orbital right here, which is called the dx squared minus y squared, looks like the previous 3 that we talked about. Notice that these lobes lie along the axes, and the last one, the dz squared, is actually along the z-axis. All right. So I know that these orbitals have relatively complicated looking shapes compared to the s orbital and the p orbitals that we talked about before. But one thing that we know about them is that they all have, originally we're told that they all have the same energy. All right. So recall that when we were doing the orbital notations, when we ever got to d orbitals, we always showed the 5 d orbitals having the exact same amount of energy. All right. So this would be for example, for essentially a naked copper 2+ ion. All right, and notice I have not shown any ligands around this. All right, and if there are no ligands around this, all of those d orbitals would in fact have the exact same energy. All right, but what is described as happening in this theory is that when a ligand comes in and makes a coordinate and tries to coordinate with the metal atom, it essentially changes the shape of 2 of these orbitals. All right, those ligands are going to slightly change the shape of this orbital right here, the dx squared minus y squared, and this one right here. All right, and when it changes the shape, the reason that it changes the shape is that there's electrons in these orbitals, and those electrons get repelled by the electrons in the lone pair of the ligand that's trying to coordinate to it. All right, so when the ligand tries to coordinate, it changes the shape slightly of these 2 orbitals, and that's going to end up changing the amount of energy of these 2 orbitals. All right, so For example, when water coordinates with that same ion to make this complex ion, what ends up happening is that those two orbitals, which I just referred to, are going to have a slightly have a slightly higher energy than the other three orbitals. All right, and that's what's referred to as d-orbital splitting. All right, whereas before all of the orbitals were considered to have the exact same amount of energy, when you have ligands coordinated to that metal, your d orbitals now have 3 of the d orbitals at a slightly lower energy level and 2 of them at a slightly higher energy level compared to the energy level that if they were all the same. Notice that the 5 all the same, when it's not coordinated, that energy is somewhere between the energy of these guys right here. So the way it's described, we say that the lower energy ones are stabilized, the higher energy ones are destabilized, and this is going to have an important effect. So whenever you have ligands coordinating to these transition metal ions, you're going to get some amount of d orbital splitting. All right, the difference in the energy between the higher energy and the lower energy depends on what the ligand is. So for example, this complex ion versus this complex ion right here, and the only difference between these is that in this one right here, your ligand is 6 water molecules, and over here it's actually, there should be a 6 right here, would be 6 ammonia molecules. But notice that when that happens, the energy difference here is much smaller than the energy difference that you're going to see for the complex that contains the ammonia. And there's a name for complexes that have a relatively small difference in their energy between the d orbitals and ones that have larger ones, and that is that when the difference is relatively small, we call that weak field splitting. When it's relatively large, we call that strong field splitting. All right. So an example of a ligand that would give you weak field splitting is a fluoride ion. All right. So when fluoride acts as the ligand, you could end up making this complex ion. Notice here that the ligand is actually a single atom rather than molecules like we've been showing before, but recall that a fluoride ion has lone pairs on it, and therefore it can act as a ligand. All right. So in this case right here, your ligand are cyanide ions. All right. So notice the difference. This is a really big difference in energy. This is a relatively small difference in energy. That's why we call this weak field splitting, and this is strong field splitting. All right, so there's an important difference between these, in that in both of these complexes, we're going to have the same number. That central atom is going to have the same number of electrons in its d orbitals. It's going to have a total of 6. All right, so what ends up happening is that here the difference in energy is so small that it's really not a big deal to put some of those electrons in the higher energy level. All right, we're very used to putting electrons in the lowest energy place that's available, but if that energy difference is very, very small, you can actually end up getting some of those electrons in their resting state to be in that slightly higher energy level. All right, but if we happen to have a really big difference in the energies between those orbitals, well, asking one of these electrons that's way down here in energy to go up here is asking a lot of it. It would much rather stay in that lower energy orbital. So even though these complex ions might look similar, the difference in energy has a big effect on where those electrons choose to reside. So if you wanted to figure out whether a particular ligand would end up creating weak field splitting or strong field splitting, one thing that you can do to predict that is to use this thing called the spectrochemical series, which is located on in your data booklet in in chart 15. All right, so if you take a look at this relative order right here, the further to the left you go, that is going to be a ligand that creates weak field splitting. All right, so you're only going to have a very small difference in energies between these upper two and the lower three. If, for example, your ligand was an iodide ion. All right, the further to the right you go, the stronger or the bigger the difference is, the more likely it is going to be strong field splitting. So notice this is cyanide right here, and if we look at that series, we notice that cyanide is something that's very much to the right of that, and that would be expected to give a really big difference in the energy. So one question to look out for would be if they had a ligand that had bromine as, or sorry, a complex that had bromine as the ligands versus say water, which would you expect to have a bigger difference in the energies. You would expect to have that with water. So we mentioned the weak field and the strong field splitting. One, and that has an effect on where the electrons would choose to reside. One property that creates is what's called paramagnetism and diamagnetism. All right, so a material is considered to be paramagnetic if it has unpaired electrons. All right, so notice that if you've got this situation like this where some of these electrons are in these upper energy orbitals, you have a couple of these electrons which are unpaired. All right, and that's going to make that material paramagnetic. But if they all choose to reside in the lower energy orbitals, and that would only happen in strong field splitting, notice that all of the electrons are paired. They've all got electrons of the opposite spin in the same orbital with them, and essentially that makes them what's considered diamagnetic. But the most important or interesting property that is created by this field splitting is the property that gives these compounds color. All right, if you have any of these complex ions dissolved in water, it's going to have a pretty intense color. All right, and that color is directly related to this. And I'm going to link a video which does a pretty good job of explaining that property.